So, hi everyone, and welcome to today's webinar organised by JetBrains. I'm Jodie Birchall. I'm the Data Science Developer Advocate, and I'll be your host. So the topic for today's webinar is how to leverage data science to improve micro-mobility use, and it's presented by my two guests, João Matos and Diogo Valente, Polónia. So welcome, João and Diogo.
Hello. Thank you for having us here, and the names were pronounced perfect.
Thank you. I had a meeting with these guys beforehand and I worked so hard on pronouncing these names. So thank you so much. Awesome. So João and Diogo are joining us from the sustainability research group Holin. This is a really cool organization that works with government groups to come up with clever solutions to environmental problems by using data science, which obviously is very interesting to me. So we're going to be talking about one of their projects today, but would the two of you mind telling us about some of your other work?
Yeah, so I'm actually not from a sustainability background. I'm studying biomedical engineering. I'm doing my master's on that. So my past work is mostly related with health data. And I started working with this kind of sustainability projects because I was really interested in data for good and using data science for projects and things that could have an actual good impact in the world. But maybe you can explain a bit more about this and how he's actually working on this right now.
So yeah, I'm from another engineering field. I'm from industrial management engineering. I'm still finishing my master's. Like João, I'm going to do my master's thesis next semester. And we got together because our common interests in sustainability. We started as a group on a few competitions. We'll talk a little bit about that later. And right now we're just seeing how can we further this kind of projects into any kind of space inside sustainability. In my personal experience, I'm right now I'm in Santiago de Chile doing an exchange, and I'm actually diving into more public policy towards sustainability and evaluating. For example, I'm doing a project to evaluate actually how do shared bicycles influence car usage in Santiago, which is amazing, and we love doing these kind of projects.
Do you know, it's interesting. We never actually discussed this beforehand, but my background is also in health. So my postdoc was in biostatistics. We're basically looking at how we could improve the outcome for people admitted to hospital with like heart attacks. We basically found that, you know, a few tweaks in how the doctors, you know, followed the protocols could save something like 400 lives a year, and that's in Australia. So that's quite a lot of lives. So yeah, it's I think we have a lot in common in terms of our backgrounds and our interests in how to use data. So great. Yeah. Sorry, no, you go.
We have some left. What the project you were just describing is actually really close to what I'm doing right now. So I'm also assessing outcome disparities in hospital admissions in the ICU. And I'm specifically looking at different ethnicities and how white people are better treated or not when compared to non-white people. So that's pretty cool.
It's super interesting. Like you probably found the same in your research, but we found a massive gender disparity. So we found that women tended to have worse outcomes. This stuff is very subtle, very interesting, very social. So cool. So yeah, I was super lucky to meet these guys at PyCon Portugal. I got a bit of an overview of some of the work that they're doing in terms of sustainability research. And it was the first year actually that PyCon Portugal was running. I thought it was a really great event. How did you guys find it?
Yeah, it was amazing. It was the first time that PyCon Portugal happened. We got lucky to have our talk there with you, Jodie, and it was very interesting to see very different talks happening. We were talking about sustainability. Jodie, you were talking about natural language processing. There was also another amazing talk. I think it was Max, his name, that was about legacy systems and organizing your projects. So it was a very interesting experience. We got to talk a little bit more, and we're very grateful to have met you and to have met all of these amazing people there. I'll definitely recommend it for next year if anyone who is listening to us wants to join.
Yeah, and I think it's going to be in like another beautiful city in Portugal because they're trying to change from place to place. So, also a great excuse to go to Portugal, which is an amazing place to visit. Would you actually believe that was Max's first time presenting? I could not believe it. He was amazing.
Yeah, he was truly amazing. No, I had no idea it was the first time, actually.
Me neither. Cool. So I'm super excited about this topic. I'm really excited to see you guys do a deep dive on it because I just heard only a little bit about it at PyCon. So let's jump into it. The first thing that we're going to do is a little bit of administration. So we like to keep webinars as conversational and as interactive as possible. So if you in the audience have any questions or issues during the webinar, please do let us know using the chat in YouTube. I'm going to be keeping an eye on the chat all throughout, and we're going to have a couple of pauses where João and Diogo are going to answer your questions. So please don't wait for the end. Do ping those questions as they come up and we'll answer them. And then also please be aware, this webinar is being recorded currently, and the recording is going to be available right after the webinar ends on YouTube. So if you have any points that you want to save or revisit from the webinar, that recording is going to be available for you right after we finish. So with all this out of the way, all the admin out of the way, I'm going to get out of the way, and we're going to hand over to João and Diogo, and they're going to show us how they've used data science to get the best use out of e-bikes and scooters.
All right, Julie. Thank you so much for that introduction. Let's go right into the more serious stuff then. We'll talk about how to deploy micromobility with this kind of macro concept behind it, while leveraging data science for more impact. But before we can do that, let's just have a look at what sustainability problems we have out there in the world. And if we start with mobility, the undisputed winner in CO2 emissions right now is the passenger road vehicle sector, which means your car, your sibling's car, your parents' car, the taxi or Uber, and even the bus. And in some cities, urban car pollution is already responsible for very unhealthy air quality and deep smog, which is actually something that I'm experiencing right now in Santiago de Chile. And to fight this, many micromobility solutions have appeared. But why then aren't we seeing transit-free cities, right? Are people replacing car trips for scooter trips? Are they just using them when they don't want to walk? This is one problem. We have others, street crime, for example, if we talk about human comfort and harassment. The stats here are impressive. Violent crime fluctuates a little throughout the years, but it's always at high levels. And sexual harassment has been felt by most of the population. And could we build more granular indices on safety like this on street or block level, provide better responses to it? And also on pollution, the next slide, yes. On waste, it's expected that global waste will increase greatly until 2050. In 2016, just the management of waste, and I'm not even talking about what's involved in actual production or disposal of that waste, was responsible of 5% of global CO2 emissions. And this is only expected to increase in the future. It leaves us wondering, are we being as efficient as possible at managing our waste? Right? But cool. Now the question is, what does any of this have to do with this, in case this webinar on micromobility and data science? All of those plots, I don't know if you saw them, were generated with a Python package, matplotlib, if you're aware of that. But besides that, is that we can start trying to tackle these problems with data science, and we are here to tell you a little bit of our methodology, how we got there, and João will tell a little bit more about that.
Yeah, so today we'll talk about how these problems can be tackled with a simple yet robust methodology. We'll go through a bit of the untapped potential of data science and how to deliver actionable sustainability insights from data, from very noisy big data. We're also presenting to you some real-world projects, in this case, the micromobility promotion at a city level, and how this methodology can be used with data science and Python and machine learning and optimization can be used towards this mission. And finally, hoping that we can raise some awareness among you and motivate you to contribute to this mission, we're going to share with you our most recent projects and hopefully get you together on board. So data science is all about a lot of things right now. I'm pretty sure you've heard of these big names here, analytics, AI, optimization, and these are being used in business context at a huge rate. Companies have been leveraging data science to optimize their processes, generate valuable insights, and create products. But what about sustainability and public policy? Sure, we see a lot of applications on business, but when it comes to public decision-making, management systems, urban planning, and so on, the real impact of data science is rather scarce. Today, we witness a big gap between what can be done and what is being done. And to do it, we need to bring together data scientists, sustainability experts, and public policy makers so that we can get together, cooperate, and apply this common know-how to make the world a place a bit more sustainable. We dare to go a bit further and say that it's about time that governments and businesses start recognizing that data science can be used in the area of sustainability with great impact, rather than just being used to generate more and more profits. So let's get started and understand how to go from these very big, noisy spatial data to the point where we can actually deliver actionable insights with real-world impact. So step by step, we'll go through geospatial indexing, then feature engineering, after that predictive modeling, and finally optimization algorithm. Of course, all of this can be done using datalore's fantastic set of features, and we'll eventually get there. In the way, we'll show some of the most handy and useful Python packages and tools that can definitely help us in the way. And let's get started. So the first step to analyze large spatial data sets and aggregate features is to split the main geographic area into smaller units over which we can summarize and aggregate these spatial variables. In some cases, we already have this done for us. We have districts or parishes, counties, but sometimes we want more granularity being brought to our data, or maybe we just don't have this information. So we really need to create this data structure that is able to accommodate our features and give us a tool for us to work upon. We need a flexible and versatile way of doing that, and an hexagonal grid is a way to do it. This is actually something that is not new, and we didn't create it at all. It's something that companies like Uber are using to accurately locate nearest drivers and estimate prices, among other things. Tabular is a very nice package in Python that allows us to do this. We can create an X grid to cover a geodata frame. The granularity is adaptable, and hexagons can be clipped by the boundary. So we have a lot of flexibility going on, and we can decide the size of our hexagons, how the features are aggregated, and so on. But you may wonder, why hexagons? Well, hexagons are one of the few shapes that can tessellate perfectly. Well, squares and equilateral triangles can too, but hexagons are quite special in that. But what's tessellating really? Well, it's covering a whole area of space without any gap or overlapping, just using the repeated use of a single shape, as you can see in these figures in the bottom. So hexagons are special for us because they are the closest to a circular shape, which reduces distortions, and the centroid of each neighbor is equidistance, which is preferable for models and problems with connectivity and movement paths. Okay, I don't know if you ever read this sentence. A famous person once said that every block of data has a statue inside it, and it's our job to discover it. Well, maybe it was not exactly like this, but with this first stage completed, we can now get creative and treat our raw data to build a created set of features. GeoPandas is a very powerful package for that, and it makes working with geospatial data so much easier. We can perform any kind of spatial operations and with geometric types, and we can calculate distances, overlaps, etc. So imagine that we want to know where to have these optimal drop-off points for scooters in a city. It might be useful to know where's the closest metro station, or where the places we want to connect are, and how many stops are in each cell. So we want to have all of this information in our cells. And GeoPandas gives us a set of tools that can perform these operations, from calculating distances to check if shapes overlap or intersect, so that the process is really easy. So let's look at a very easy example to understand these kind of things. On the left-hand side, we have a location of green areas in a city. And this is just raw data. So we have the areas and the coordinates, and we're plotting them over the map of the city. But if we apply this kind of strategy and we create our hexagonal grids and calculate our features when it comes to proximity, in this example, we can get the right-hand side plots in which we see the proximity to each green area in each cell. And this is quite powerful if we want to apply predictive modeling and optimization algorithms on top of that. Of course, this reasoning can be applied to all sorts of different challenges and spatial data. We can do this with metro stations, bus stops, and so on. Okay, so now that we have the features, let's do some machine learning, also known as magic these days. And as you probably know, there are several types of machine learning. We usually use supervised learning, which means that we have the labels and we have ground truths. So we know what are we aiming at, but we could go for unsupervised learning, semi-supervised learning, self-supervised learning. Well, let's just not get started with that. So focusing on supervised learning, we can have two big buckets of things going on. We can have classification, where we want to classify according to discrete values, or we can have regression, where the output is a real number. We have a continuous outcome. Inside classification, we can have binary classification, which means that we just have two classes. So we're aiming for zeros and ones. And a good example of that would be which micromobility solution is most likely to be chosen by a user, scooter or bike. On the other hand, multi-class classification allows us to bring more than two classes. We can have 3, 4, 5, as many as you want, really. And an example of it could be what is the expected usage of micromobility solutions in this region of the city, low, medium, or high. And if you want an example for regression too, we could have something like how much CO2 emissions are saved when doing this trip instead of micromobility, instead of a car. And this would output us the kilograms of CO2 that are being saved. For any of you that have already played with AI before and have trained a machine learning model, you're probably quite familiar with this. So let's say that we want to build a random forest classifier. We need to do some hyperparameter tuning. This is actually fundamental in the pipeline because we can have either catastrophic results or fantastic results. So to do it, we just create a grid with the parameters that we want to optimize. And for each parameter, we're setting a range or a set of values that we want to test. And with this very handy, neat function from scikit-learn library, which is grid search with cross-validation, we can combine all of these parameters and test all of them in a huge batch. And we're iterating over all of these parameters over different folds. So we're taking our train data, we're setting some data apart for validation, we're training our models with each one of these combinations of parameters, and then we're choosing the model that performs best in the validation set. Of course, this is very handy to get a trained model, but we can only know if our model is actually good if we test it and if we compare it with untouched data that has never been seen before. And this is the test set. The test set is kept apart for the whole process, and in the very end, we are going to use the best parameters from the previous step, and we're doing our predictions, and then we can use whatever metric we want. In this case, we're using an accuracy, but we could be using a F1 score, a precision, a recall, or some more complex metrics. And with these results, we can actually know if our model is performing well or not in this unseen data. Other examples could be a confusion matrix, as you can see here on the right-hand side, with a more visual dimension bringing in, or a rock curve, which can give us these insights on how our model performed. But no one really likes a black box, right? We are all interested in knowing which features weigh more in a model. Would we trust a model if we didn't know which features are taking the most importance? Could it be the case that we are bringing harmful biases to our decisions if we don't know the features? I think that's a reality for sure. And more than ever, the machine learning community is worried about that. So we really have to make sure that we can make our conclusions fair, transparent, and explainable. And there are a couple of ways of doing that. One way is looking at feature importance, which we will focus right now. Some models like the random forest classifier make it really easy for us, and we can just take the features importances out of the model by assessing the impurity of the leaves. And we can actually see what characteristics of the data are contributing more to the final predictions. So if you see here on the right-hand side, the feature of distance to a nearest attraction has the most importance. So scooters are most picked up in these downtown zones where we have attractions for tourists, which kind of makes sense. And this is interesting as a sanity check for our model. If we want to go a bit further, we can use a package called SHAP, which is based on the model, which is game theory based to disclose features individual contribution. It stands for Shapley Additive Explanations. And it is a bit more interesting because it gives us not only the feature importance, but the direction of the contribution. And as you can see here, the distance to the nearest attraction is, again, the most important feature. But now we get to see how does this affect the model. And you can see that the high values are on the left-hand side. So the lower the nearest attraction distance is, the higher will be the likelihood of having a scooter or a bike being picked up, which really makes sense. So the closer we are to an attraction, the higher the probability of having this micromobility use. Okay, so we moved from having lots of data, spatial data with a lot of noise, a lot of missing data. Now we added more data on top of it with the forecasting layer. And we want to make reliable and trustworthy decisions to deliver actual impact. How can you do that, Diogo?
That's a great question. And to answer that, we must go from what we've been looking at, which were predictive models, and we need to enter into the prescriptive models. And what are those? Well, we have a lot of possibilities to talk about as well. Let's see some of the most maybe used ones and simpler. We can start with mathematical programming, where we maximize or minimize some mathematical function by changing decision variables in regards to some constraints. In other words, we study optimum intersections. It can be linear or non-linear functions. And to answer questions, for example, like how many scooters or bicycles are needed in each zone to maximize CO2 savings. But you can also rely on graph theory, where we take a finite set of solutions, we graph them, and we apply a bunch of algorithms to answer questions, for example, like what is the safest street route for people while walking to minimize street crime? And finally, you can enter into the uncertainty realm, where you don't know what's going to happen in the future. And we are talking about stochastic optimization, where we have some source of randomness or uncertainty that we model through some kind of distribution. For example, which would be the best dark corridors to place in a urban city while considering bats' flight patterns at night that change throughout the years. Right. So let's try to apply this methodology, all of that João was talking about, to a specific case in shared micromobility. So we start by stratifying our geospatial zones. We identify features associated with higher usage, like João said, for example, the distance to the nearest bus stop. And we predict predisposition of each people or of each zone to transition from car to micromobility. Now the question is, how many bikes or scooters should be available in each zone? And we can answer it with a simple linear programming model. Anyone who's into optimization techniques, this is one of the first things that you learn. And you can use Pulp, which is a very useful package to solve these kind of problems. And we initialize the model and start appending the decision variables. In this case, the number of scooters and number of bicycles in each zone. Our objective then, in the next slide, is to maximize, and we are here talking about sustainability, so we are not looking for profits, we're not looking for usage by itself, we are looking to maximize the CO2 savings produced by by every trip. And now we are ready to run the model and find the solutions, right? And if we do that, well, the model will tell us, hey, just place infinite scooters and infinite bicycles, and you'll have maximum CO2 savings and problem solved, right? Something's wrong, and that is on the one hand, budget reasons. But even if we could pay for every scooter or every bicycle possible, there's only so many that people would like to use. And here is where we kind of mix everything up, and we use our predictive modeling models for that predict the predisposition of people using a bicycle or a scooter, and we use that expected value that we created as a constraint of the number of trips, and we can get our solution afterwards. Here are some really useful packages to go into more complex stuff. I've talked about Pulp, but there is also SciPy and Pyomo, which is also very, very interesting. On the for graphs, we can have iGraph, GraphTool, NetworkX, and if we want to deal with more larger scale optimization, and even for optimizing machine learning models, we have Gecko, TensorFlow, and PyTorch. This case study, what I've just talked about, was one of our first case studies together, where we were trying to promote Matosinhos, which is a city in Portugal, transition to micromobility. We predicted CO2 emissions, we predicted the predisposition of each people to use a certain device, and we optimized the placement of those zones. And we expected that with the new placement, up to 73 tons of CO2 emissions could be saved per year, considering only a penetration rate of 5% per zone. And before I move on, let me just ask you, anyone, if there are any questions, please feel free to ask them in the chat, and we'll get right into it. If not, yeah.
I actually have a couple of questions. Sorry, I'm being rude and asking my own. So I guess geospatial data is pretty dense, even for one city. And you need to kind of do this trade-off between how granular your geohexes are and then how big your data is going to be. So like, how did you make that trade-off? And like, how did you manage data of that size? Or was it not that big?
We were lucky enough for the most of the case studies to not have a huge data set, but we'll see, for example, and João can add another thing afterwards, and we'll see, for example, on the notebook that we're going to show you, that one of the things that made us decide on grids, on the grid size, is, for example, the number of drop-off points that are in each zone. So we didn't want to have 100 drop-off points per zone, and we didn't want to have everything to be zero. We established it, and we'll talk about it later, for bias, for avoiding biases as well in estimations, to have mostly one drop-off point per each zone of the grid. Maximum. I think we have 2 maximum at the point. But that's the kind of analysis that you do. It's very empirical. It's you go through the data and you make that kind of decision. João, do you want to add something?
Yeah. So, like, theoretically, it depends on the outcome that we're working for. So in this case, the cells and the granularity of the data must match the feasibility of having a certain number of drop-off points per zone, as Diogo was saying. But unfortunately, at the end of the day, it's a bit about the amount of data that we have. And sometimes there's a certain variable that we really need to come to play, and we don't have enough granularity for it. So we kind of need to set that as our like maximum granularity we can go to, which sometimes it's not that as big as we would like to. But let's say that there are some data that we just have at the county level. Sometimes we're limited by that. And unfortunately, that's something that happens quite often when the data is not super abundant.
Yeah, I remember that again when I was doing my postdoc. I had to augment the hospital data sometimes with stuff from the Australian Bureau of Statistics, and sometimes the granularity was like not that good. So it would be like multiple hospitals get the same values for things. You're like,
Yeah. So let's say that you have 4 hospitals in the same district, and you only have like the average income of like one value for that district. All of those hospitals are getting the same value. That, well, that's a shame, but it's what we can do sometimes.
Yeah, and sometimes close enough is good enough, right? Like,
Yep.
Yeah. We did have another question come in. So can the aforementioned limitations regarding the cost of the bikes and the number of people be optimized using simplex?
Yes, that's actually what the model does. In this case, it's a linear programming model. So Pulp uses simplex for optimizing the placement.
Awesome. And yeah, I guess you'll be able to show us that when we get to the code. I had one more question, which is, so I find it quite hard to understand what 73 tons of CO2 looks like. So what would that be the equivalent of in, say, I don't know, car rides, or maybe I'm putting you on the spot and you don't have any sort of gauge. Sorry, please do this calculation. But like, do you maybe have a yardstick for comparing?
That is an amazing question that we should have prepared beforehand.
I'm sorry. No.
João, do you have
yeah.
any idea of the trade-off? What the trade-off is?
I was trying to check on the internet like Chile's energy consumption, but I didn't have time for that. But yeah, I don't really have an estimation on how much that is, but I think it's quite a lot.
Yeah, I think that's fine. I just wanted a sense of like, is it a small amount? Is it a large amount? So yeah, cool. It's
reasonable, I would say.
Mm.
And another thing to point out, in most of these sustainability projects, we usually deal with CO2, but sometimes it's not actual CO2 we are talking about. We are talking about CO2 equivalent emissions, which means that we are considering all kind of gases and greenhouse gases, for example, that are saved, and we are doing the equivalent amount of CO2 because it's the unit of exchange in this market, right? But it doesn't mean specifically that is CO2 per se.
Yeah, it's just to give a sense of on a standardized metric. Yeah, makes total sense. Cool. So I think that's all the questions. Thank you so much. So let's get over to the code, to the fun bit.
Just before we dive into the notebook, let me just present the project that we're going to show.
Oh, of course. I'm sorry.
Yeah. No, it's completely okay. We are also talking about micromobility here. In this case, another city in Portugal. I don't know why all of our micromobility studies were in Portugal. But in this case, we're trying to optimize the drop-off site points in the city, right? And we used a random forest classifier and then SHAP to analyze the most important features for scooter usage. We scored each zone according to that models, and then we optimized the locations. And here, the impact was not so great as we did in the other cities example. We increased the number of usage by 10,000, which is a rather humble 2.5% of increase, which on the long term, of course, makes a difference. So let's deep dive into the notebook. Here it is. We can see João is over here trying to support me in this presentation. This is also a very cool feature of datalore. It allows us to have collaborative work here. Hello, João. But let's dig into it. This was part of the World Data League, a datathon competition organized between February and April, I think. We did this work with 3 other amazing colleagues: Cristiana, another João. João is a very common name in Portugal, as you might understand by now, and Patricia. We'll quickly go through the data we had. We see how we constructed the features and classified the zones, and we'll also go through the optimization model and the final product. But first, of course, we need our packages. We have a lot of them. We base our data frame analysis in pandas, and of course, for geospatial data, GeoPandas, as João talked about. And we use for the models the scikit-learn package, and pulp for optimization, also shape for interpretability. And our visualizations, matplotlib always with Seaborn coupled to it, and that's it. So as regarding the data we had, urban transport data provided to us, and we fetched some other relevant data we thought on interesting attractions in the city, schools, universities there. We didn't use demographic data in this specific case, as it was not readily available for the case study. And another thing that I would like to point out, we selected this case study for a very special reason. First, it was one of our earlier projects, so we were still beginners, and so it's very, very simple. There's very simple models, but it also shows that you don't need complexity to start thinking about this kind of problems and start working on them. So our analysis starts with building our geographical grid. Again, as we were beginners by then, we built squares. If it was now, we would have built hexagons. And this was done within another Tumblr package back then. This was done using GeoPandas and a little bit of math into it. And this is what the city of Porto looks like with squares on top of it. And on colors, it's different packages, different parishes, sorry. We then dive into the features. Let's look at bus-related features first. We use general transit feed specification dataset, which has all the frequencies, all the number of lines, etc. on the dataset. We calculate bus frequencies first. We then go into the unique bus lines passing to by each bus stop. And then we construct the features that we're going to get into our grid, into our data set for the modeling. One of them is the distance to the nearest bus stop from the centroid of each zone. And the other one is the number of unique routes to cross that cross each zone. We repeat the process for a bunch of other features, like the metro features, bicycle paths through the city. You can see them here, points of interest, etc., etc. And we finally look into the trip data. I hid the code here because otherwise it would be super all over the place. But if you are interested to check it a little bit out that later, it will be available on our GitHub page, and you can also ask questions about it. But if we look at the scooter trips, we do some processing here as well, and we count the number of trips done in each zone. And I was saying before, answering Jody's question, we count that the number. I'm sorry, I was talking about the drop-off points. Actually, we are still in the trips. Sorry for that. And if we are considering the trips, you also do a little bit of analysis, considering how many trips start in each zone, for example, and for us to afterwards build a more specific data set. This is what it looks like, the number of trips that are generated in each zone. We can see that most trips are generated in the city center, and a little bit here near the river and near the ocean, which is also very intuitive. And now, yes, answering to Jody's questions, when you look at the drop-off points, and this is something that we iterate the process, we analyze it, and then we build the grid and things like that. And we find that in this case, the number of the max stops per zone is 2, but most of them, these are the stops, but most of the zones have only 1 stop. There are 210 stops, drop-off points in the city in this case, and now we are able to go into the classification phase, and a very important thing also to avoid any biases in this case is to analyze well the data. And because of course, if a zone has more drop-off sites, it will have the tendency to have a higher number of trips generated because of it. So we select only the 204 zones which have only one drop-off point. And this is just that pre-processing. And now, of course, we need to split the data sets into train and test. The test is that component of the data that is never seen before by the model, where we test actually the accuracy and all of other metrics available. In this process, we train two different models. We train a logistic regression for classification, and we train a random forest classifier. Another important thing to note here is that this is also a technique that will allow to yield better results. We divided the classification only into two classes, so it's a binary classification. Either the zone will have a high number of trips generated, or the zone will have a low number of trips generated. We did this to increase the performance of the models, because in this case the data for simple regression that would estimate the actual number of trips, so the continuous number of trips, would be too noisy and with low results. So we built classifiers instead on those two classes. We of course start with hyperparameter tuning, and we do the 5-fold cross validation, which basically is testing the data multiple times, and we then select the best performance, right? And in this case, the logistic regression has an okay accuracy, quite low, 56%. But if you look at the random forest classifier, which is a little stronger, we get a little bit better, 66% of accuracy. We go with this model. This is also important to test different models in your data sets to see which one is more reliable. And now we are able to interpret the results. As João talked about before, the random forest classifier has a very does this for us very simply, and we can see the importances of each feature. But of course, we want to go a little bit further, and we use SHAP afterwards as an explainer, which also very simple commands, and it outputs this graph. We can already see some incongruences between the graphs. For example, if we look at the random forest classifier, how it explains their features, the distance to the cycle path here is very important on the second place here, but SHAP brings it down a few positions. And this is also very important especially when you're dealing with demographic data, but still we want to be able to interpret well our results. We are now then in a position to build our zone scores, and this is some also pre-processing here, magic to scale and standardize the importance of each feature. And with this, we built our final score, and voila, here we can see how it looks like in the city. Again, we can see that the scores are highest in the city center, but they are a little bit more dispersed than if we just looked at the trip generation. Right, so let's go into improving the location of the drop-off points now. We start by placing our 210 drop-off points by zone score, and just to see what happens. So we basically order the zones according to the scores we created, and we placed it by them, and the results are not surprising at all. This is what happens. In blue, we have the new drop-off points, and in yellow, we had the old ones that got removed by this, and everything is focused on the city center. And of course, this is not optimal, because we want accessibility in the whole city. So we need to do something else, and this is where the optimization comes in. This is a twofold process. We create a model that spreads the drop-off zones equally according to a reliable minimum radius, and then we populate with the drop-off points we have left according to the scores. So we build the minimum radius between the drop-off zones. And how do we select it? Also some data analysis. We plot the distance traveled, the frequency. This is actually the frequency, the number of trips that traveled in between 0 and 1 kilometers. And we find that distances are skewed to the left, which means that most trips were of low distance. And we use the first quartile of distance travel to create our radius, which means that we want at least a 400-meter radius between stops. So because less than that, people won't travel less than that, or most people won't travel less than that. And now we create the distances between each zone. And for example, a radius is here in red. We do this for each zone. And then we build a model using pulp. So this is what building the model looks like. We create it. We add the decision variables, which is a binary variable that says, hey, this zone has a drop-off point, or this zone doesn't have a drop-off point. We add the restrictions of the radius. And we also had a restriction for parish to make sure that every parish has drop-off points. And our objective here is to maximize the score. So we are maximizing the total score on the city. We solve it, and it gives us something like this, a little bit more dispersed. In blue, the new ones. In yellow, the removed ones. So we can see that they are not, most of them are not in the exact same position, which means that there is a lot of place to improve the positioning of these drop-off points. We still have 110 stops to input left, and we just filter through the score we created. And then finally, we get this beautifully dispersed positioning in blue that has the perfect placement of drop-off sites that maximizes trip generation while also allowing general city access. We then made a simple product demo to be used for decision making with this case study, where users could change a little bit the importance that they would give to each factor empirically. Of course, our models output those importance, but it's also important to have human interaction, human feeling into it, in order to avoid those biases that we're talking about. And then it outputs the final positioning of those drop-off sites. So this is it. We also estimated impact through the scores, and we have other EDA afterwards. Again, if you want to go back more into the code, this will be available in the GitHub. You can also ask questions about it. But right now, after this presentation, after this notebook, you guys might be wondering, all right, fine, that was cool, but does this actually work? And if you could go back to the slides just to tell a little bit more about our latest project. We dare, yes, to say yes, that it works, and we'll show you how we have been doing it with real case studies. We are a team of 4 right now. Again, João, Patricia, João, and me. And we are 4 like-minded Portuguese friends, sometimes spread around the globe, as we are right now. I'm in Chile, João is in the United States, the other 2 friends are in Portugal, and sometimes we come together to do stuff like this. We participated into different datathons, one in Portugal, and the other one was worldwide. We were lucky enough to win them, and they all want to apply data science to make cities around the globe more sustainable, always with the United Nations Sustainable Development Goals in perspective. With the goal of using this kind of data to deliver real impact and make the world a little bit more sustainable, we came together as Holin to participate in this kind of competition, to do our own research projects, to work and ultimately to help institutions, companies, and governments use data for sustainable development. And we are always looking for new challenges, new ways to learn, for people to tell us, hey, you should have you tried this model, have you tried that thing? So we are very open to that. We are very open to learning, and we are very open to contributing to a better world and change. So feel free to reach out if you have anything to talk to us about. Thank you so much for your time.
Thank you. It's super cool, and like what I really like is the fact that you thought about, okay, well, if we have all of the bikes concentrated in the city centre, it's not actually going to be that useful. One question I did have is, okay, so one of the constraints you used was price, and another that you used was basically was price the only constraint, or was there one more?
On this specific case, we talked about two different cases. On the first one, it was the budgeting and the predisposition to use the scooters. But on this case, on the notebook that I've showed you, it's a little bit different. We just picked up the drop-off points that already existed and shift them around the city. So there was no budget constraint that we were worried about. We restrained by the minimum radius between the zones, and also by the minimum number of drop-off points that we wanted in each parish.
Got you. So you've talked about minimum drop-off points. So one thing that I suppose people talk about a bit with e-mobility solutions is the amount of bikes or scooters that you might have like clogging up the footpaths. Obviously with the drop-off points, it's a little bit different. But I've been to Porto and I know how narrow those streets can get in the old city. Is this something that you would sort of have changed, or like, I don't know quite where I'm going with this question, but like the density of those devices in maybe areas where the streets might be more narrow, would this be something you would build into future models? Like, could you even get data about that?
Yeah, definitely, that's a very good point. Yeah. So in these problems and these projects, we didn't have really data to approach that. But it would be very interesting to bring that to play. Another thing that we could have done, but again, we didn't have the time nor the data, would be to say, okay, there are certain types of flows that are very typical in a city. And I have that experience myself here in Cambridge. So we have bikes in the dorms and bikes in the university. So people tend to get the bikes in the morning from the dorms to the university, and vice versa in the evening. So I know that if I leave home too late, I'm probably not getting a bike. And if I leave work too late, I may have the same problem. So there has to be some person or some service that gets the bike countering this flow, and I often see those people doing their work. And there's a lot of room for optimization there. So if we took into consideration where the bikes are being picked up and dropped off, we could tell, oh, maybe we need more people doing this counter flow because this is a very typical flow. So yeah, there's a lot of room for improvement here. The density of the streets, the typical flows. It's very important to know where people are, and we could even have brought more demographic information about that. So we know that in the dorms or where people live, they're going to pick the scooters and the bikes in the morning, and where they work, the flow is totally opposite. So yeah, that's a very interesting point.
Yeah, and like I live in Berlin. It's one of those biking capitals. So I can definitely say like something like this analysis, even in the form that you did it, even without these optimizations that we've talked about, it's a city of 4 million people. I think it would definitely go a long way. We just had one last question, so let's answer that one and then we can wrap up. Would your analysis also take into account the altitude of each drop? So, for example, here in Barcelona, people just grab the bikes and go downhill.
That's an interesting question, of course, and also this kind of follows up on the previous question on the types of features. Ideally, we would like to have joined the two micromobility case studies that we showed. For example, the first one that we talked about only on the slides, not on the notebook, was we took into account the heights of each strip that were made, into considering how the CO2 emissions were saved and how we placed the scooters. In this case, it was hard for us, for Porto, to have the difference of heights, and Porto is a city very well known for having height differences. But as a final remark, to answer this, and also touching the last question behind, on one city, on the Matosinhos, we didn't have drop-off sites. We just were looking into where to place each scooter, but they could be placed anywhere, and they could be dropped off anywhere. And that allowed us to have a little bit more freedom with the trip generation and looking at where trips were started and where trips were ended. In the case of Porto, if we compare the graphs, for example, of trip generations, or where the trip starts and where the trip ends, they actually are very in line. So even though the zones that where you start and where you drop off in one trip are different, on a global analysis they are usually the same. So we decided to not input those data also in this latest model. But of course, ultimately, as much data as we have, the better the model will output, and it's always a work with also the stakeholders that are involved to allow us to access that data, which also very important for this kind of models.
Yeah, let me just add something on top of what you just said. So I think that the takeaway message here is that it's super important to really know what we're talking about, and we don't want to just be data scientists trying to optimize micromobility everywhere in the world. We really need to bring these like experts on the city, because each city has its own details and its own ways of working. And as Jody was saying, Porto is full of hills, but on the other hand, Matosinhos is by the shore, so we don't have as many hills. And for instance, in Porto, it rains a lot. So weather is definitely something that we want to bring to play, because in rainy days, maybe we don't have to have people moving bikes around because they're simply not going to be used. And on the other hand, Matosinhos has beach, and tourists may like to take their scooters to go to the beach, and then they don't care about it anymore. So we have to take that into consideration. So we really need to bring together people with expertise dealing with data, but also these social scientists and these people who know how the city actually work, so that we can have something that makes sense and is adaptable to each situation.
Awesome. So let's start wrapping up. So for those of you who are in the webinar and people watching later as well, so they probably want some more information about Holin. So you guys have already shown the GitHub page. Basically, they can access from that page all of the code from there, right? Or is there another link?
It's all in the GitHub. But we can also share the datalore link, maybe, if to actual...
Yeah.
For interactiveness and anything.
Awesome. Cool.
Yeah. Jody, let me just add something. I was searching the internet about your question, and I found out that so the 73 tons of equivalent CO2, that essentially means that we're cutting off 150 cross-country flights in the US. So if we did New York, Los Angeles, and vice versa, 150 times, we would have the same amount of CO2 being saved, which may not sound like a lot of flights, but flights like emit a lot of CO2. So this is kind of considerable. So yeah, just to answer to your question, that was unanswered.
Awesome. I love that you managed to get it right at the end. And it's more than I thought it would be. So I'm even more impressed.
Can I add just something here? Sorry, Jody. This is more
ahead.
for food for thought, and for us to talk a little bit about also the limitations of these estimations. So of course, this is what the model estimated just by switching from car usage to micromobility scooters. But of course, we have a lot of other CO2 emitting things that happen around. For example, if we want to replace the scooters at any point someone needs to grab them with a van and bring them from one place to another. These are all things that we as data scientists and when we are trying to solve these kind of problems need to be aware. We cannot just trust the algorithms by themselves and the strategy. We need to be very open to the other things that might be influencing also this decision. So that's just for wrapping things up as well, and to show a little bit of the limitations that all of these things have.
Yeah, and I think that's always such an important thing in any data science project. Like there's always some sort of constraint where the data hasn't covered it. Yeah, and I think it's important to bring that in mind, sorry. Cool. So let's wrap it up here then. Thank you both so much. I really enjoyed this. It was really, like we said, kind of going back to stuff that I used to do when I was an academic. So it was really enjoyable, super practical. And I think also exposed me to some techniques I haven't actually seen. I know you think it's a very simple analysis, but I've never done anything in optimization. So that was super cool. Yeah, and thank you again. Let's wrap up here. And
yep, thank you so much, Jody, for having me.
Thank you so much for this.
Yep.
No problem. So, bye.
Bye-bye.
Bye.
Thank you.